Swayam Prabha. Digital India. Educated India.
Welcome you to the next class on Bioorganic Chemistry, that is Inorganic Chemistry of Life with the principles and perspectives. And in the last class I have talked to you about the oxygenase, mainly the monooxygenase, and example cytochrome P450. Let us look at one more monooxygenase. Why we should look at one more? The one which I have explained in the previous class was that based on the heme. Let us take another example of monooxygenase where there is no heme involved. The most popular enzyme for this is methane monooxygenase. The title itself is methane monooxygenase 1-oxen. When you add 1-oxen to methane, what will happen? Methanol. So, it is a conversion of methane to methanol is a methane monooxygenase. So, and how easy is this? Suppose you want to make in a test tube, how easy is this? You know what a bond energy for a CH bond, because in the methane you have these 4 CH bonds. One of the CH bond you have to activate and insert O to become COH. So, to do that you have to activate the CH bond, you have to basically break that bond. So, what is the energy you think is the CH bond? I am sure you are aware covalent bonds are in the range of 100 kilocalories and CH is about 104 kilocalories. So, can one do this in the in vitro? Yes, one can do, but you require very high temperature, pressures, catalysts, many things are required. So, without catalyst, pressure, temperature is not that simple, but the enzyme methane monooxygenase quite nicely does at ambient conditions, at the room temperatures, etc., and without using any high temperature, high pressure, nothing of this thing. And it will also use O2 as the oxidant. And once you convert the methane into methanol, it is a very safe form and this can be transported. When you want to transport this energy material from one place to the other, it is dangerous to use in the form of methane, but it is comfortable to be used or safe to use in the form of methanol. Okay. So, what is the kind of a reaction you are talking about? A CH4 plus O2 plus 2 electron plus 2 H plus becomes methanol plus water. Okay. So, CH4 plus NADH, that is the one, H plus O2, CH3OH plus NAD plus H2O. So, this is what is basically is happening into this particular reaction. And if you look at the methane monooxygenase, there are two types: particulate kind of a methane monooxygenase, which means the insoluble one. The second one is soluble methane monooxygenase. Okay. And let us see some characteristics of this enzyme. Some characteristics of this enzyme is a very complicated enzyme because, or huge enzyme, because it has 6 subunits: 2 alpha type, 2 beta type, 2 gamma type. Alpha, beta, gamma, alpha 2, beta 2, gamma 2. So, it is a hexamer, okay, dimer of this alpha, beta, gamma, basically what you can say is that. And total molecular weight is that around 250 kilodalton. So, very huge. So, what it has one other thing called hydrolase portion. The hydrolase portion is the one where the ion center is there, and the ion center in this is not with a heme, but without the heme, but it is a di-ion center. So, it is called MMOH. So, this part is called MMOH. So, the ion that is present in this is called MMOH. This is the di-iron center, okay. And then you have a reductase part. So, MMOR, we have seen earlier the electrons have to come from NAD, then NAD to FAD, FAD to iron sulfur cluster, all these kinds of things. So, this is the reductase part. And there is another protein which is called MMOB. This is called a coupler protein. So, what is coupler protein? That is, whatever the electrons got activated out of this MMOR should be transferred, etc., reaction center to do the reaction. So, that means this and that should join together, as that is what is joined by the coupler protein. Okay. You will understand more now when I explain you using this one. Hydrolase, as I told you, hydrolase has a dinuclear iron center. So, you can see this dinuclear iron center is 2 iron centers, 2 histidine imidazoles and a bridge glutamic and a bound glutamic 1 and 2 of the glutamics here. Okay. And these are some internal ligands, nothing to do with the substrate, or is not a substrate here. Some other ligands, and those ligands can be replaced when appropriately oxidized, and it is connected by the hydroxy bridge. So, it is connected by the hydroxy bridge. Now, let us come to this portion. As I said, there are 2 alphas, 1 unit of alpha, 2 unit of alpha. There are 2 betas, there is 1 unit of beta, another unit of beta, and there are 2 gammas here, there is 1 here and 1 here, and so therefore, these are the 3. So, in this basically what is happening was, so this is the reductase part where the reduction electrons generating, this is the reaction part, and the gamma is coupling between the alpha and beta. So, it is a coupler. So, when something happens here, it should attach with this. If something happens and if this part of the protein is far away, then what will happen to the electron that is generated? It will get into the O2, and then O2 will be add to the activated O2 will add to the protein, and protein will get destroyed. So, when the electrons are coming out, this protein, this part of the protein should be ready, and that is what we basically mean. So, you can see FeOH, Fe is shown, and you see the NADH, NAD couple, and electron going through the FAD, then going to the Fe2S2 pyridoxine, and then going to the ion center, finally to this ion center, and then to the into the O2, and then get the OO activated, and then becomes the methanol. You can see in this also is very clear. This is reductase. The NAD will give it to the flavin, from flavin to Fe2S2, from Fe2S2 to the iron center, and that is how the electron flow. So, from here to this, this to this, this to this electron flow. So, therefore, this kind of an electron flow will ensure, so when the electron is coming out, these two should be coupled, that is where the gamma protein is there, these two should be coupled, okay, and that is what is shown over there. As a result of that, actual reaction happens at this center, not here. This is all electron releasing junction, this is where the substrate is converted to the protein product. So, this is referred as a hydrolase part of the enzyme, this is referred as a reductase part of the enzyme. So, the total enzyme you can see over there. I hope you understand that. So, diion center is the reaction center, and the NAD to FAD to Fe to S2 is the electron flow, and from Fe to S2 the electron will go to the this guy. Now, let us look at a general mechanism of these one. Okay, you have a resting state at this. In the resting state, you have a the carboxylate bridge as well as a hydroxyl bridge is there, and this one is activated in presence of the electrons. There, since there are 2 ions are there, you need 2 electrons, 1 each. So, ion 3, one more ion 3 becomes ion 2, ion 2. Now, this becomes a very active reduced form. So, this will grab oxygen, because oxygen requires 2 electrons, one from this ion, one from this ion can be given. When it is given that, then it becomes peroxo species. And this peroxo species is very reactive, it is not that stable or anything. It will break down very fast and form this Fe. One of the oxygen will go water, which is not shown here. In the next scheme I am showing what it will go water, the other one. And this immediately converts into a ferriloxo, and then that is added to the methane. So, that part is also not shown here. So, these are called the intermediate P type, which is identified, intermediate Q type, which is identified in this one. That is why this identified intermediates are being kept here, and then so at the end again. So, that is how this whole cycle. So, this is a binuclear containing oxo-bridged species, and interacts with the methane and abstracts the hydrogen and produces a methyl radical, which is not shown here, and the methyl radical in turn reacts with the hydroxyl, and which is coming from the iron, and then whole thing will convert into the methanol, and then it will go back. A more understandable mechanism with the reaction rates is shown over here. This is your starting enzyme, resting part of the enzyme, bridged ion 3, and this gets active in presence of the NADH with the reductase part that I have shown you, and that will give electrons one at a time, totally 2 electrons very quickly. 2 electrons will become ion 2. This is a reduced enzyme, reactive enzyme. This will take up O2 and convert into, initially form some complex and then break it down. So, this is the peroxo complex, and this is basically broken down. So, this part will take out basically this is from the bridging, this is from this, of which one of the O will go as water, because 2 hydrogens are there, H plus are there, and the other one is now converted to the substrate. So, the substrate which is bound in the vicinity will form a radical and then pick up this hydroxyl, and therefore, it will go into this. Now, let us look at the rates. So, initial reductase is, of course, the electron transfer is very fast, then the oxygen is a 22-second inverse, and this is, and the next one is the breakage of this peroxide, peroxo bridge to water and ferril, and that is only 1 second inverse. And then this activation of the substrate, so to form the substrate radical, that is also very fast at this stage, and then one more very fast reaction is it will keep transferring, and then the product is formed. It is the release of the product which is the weakest step or slow step. So, rate determining step in the entire process is the release of the product. So, release of the product, please kindly make a note of this. So, how did one measure all these rates? One measures all these rate, you take this enzyme in vitro and put nitrobenzene and look for this one. So, by measuring the concentrations of how much is converted, you can get the rate as a function of time. If you get do that, you can get the rate. Okay. So, therefore, this is a very interesting thing. So, first ion 3 in the resting state, then becomes ion 2 is very reactive to oxygen O2 2 minus, that will become peroxo, and peroxo is not stable, it will break down to ferryl O and water, and then the ferryl O is now very quickly breaks down the substrate CaH and then attaches OH to that, and cycle will go. Okay, I hope you understand how a monooxygenase without the heme is happening. So, with the heme, what we have seen? Ferril. Without the heme in methane monooxygen, again ferril. So, the ferril seem to be very important kind of thing. And here, what are the steps? Isolated kind of thing, intermediate P, intermediate Q, these are all understood ones. Okay, having understood the monooxygenase based on the cytochrome P450, monooxygenase based on methane monooxygenase, I think now we are graduated to take up dioxygenase, aren't we? Yes. So, in this we will take one example, proto-catechate 3,4 dioxygenase. So, dioxygenase, as I have already mentioned to you, it will break the molecular oxygen into 2O2 minus and then add both the O's to the substrate. Okay. So, some isolated dioxygenase from bacteria catalyze the critical ring opening reactions, and because of this a lot of organic products can be biodegraded. So, there are a lot of pollutions in water. So, one of the common pollution is the heavy metal ion. Other common thing is the dyes, organic dyes or this kind of thing. So, therefore, one can break these aromatic impurities from this particular water to purify water, etc., by the ring opening mechanism, and their dioxygenase is the one which is acting actually. Okay, these bacterial enzymes generally contain non-heme ferric ion as the sole cofactor. There is no heme at all. Proto-catechate 3,4 dioxygenase was one of the first such enzymes recognized and catalyzes the intradiol cleavage of the proto-catechuic acid to the oxygen by the oxygen to produce beta carboxy cis mucanic acid. So, protocatechuic acid to the cis mucanic acid. So, there are quite a few structures are known. X-ray structure of the 3,4-PCD reveals the catalytic ion required environment required for oxygenolytic. So, oxygenolysis basically, you can call it as oxygenolysis, cleavage of aromatic rings. That means when you are adding the oxygen, the double bond is broken. That is what it basically means. Oxygenolic cleavage means of aromatic rings, and also provides a novel holo enzyme assembly with some very high symmetry and cubic 2-3 symmetry. Okay. And first example of the mixed beta barrel domains. So, this is intradiol dioxygenase with two where both the oxygens are added to the substrate. So, this has an alpha beta dimer. Alpha has 22 kilodalton, beta has got 27 kilodalton, roughly about 50 total together. There are 12 such copies, 12 such alpha betas. So, 12 into 50 is 600. So, 12 into 1 less. So, therefore, 580, 590. It forms a quaternary structure in total. So, you can see that. So, you can see some in the front, some on the back side. So, totally 6 and the 6 totally is 12. So, each one has a pair alpha and beta, alpha and beta, alpha and beta, alpha and beta. So, like that you have a 6 combination 6. The reaction center is at the interface mainly into the beta subunit. So, alpha subunit, beta subunit. Okay. The reaction center is at the interface mainly into the beta subunit. Tyrosine to ion 3 charge transfer. And one another important thing is you can see the center here. So, there is one tyrosine, okay, and the histidine and another tyrosine. So, therefore, this tyrosine gives a tyrosine to ion 3 charge transfer. So, it is a charge transfer kind of thing. So, therefore, one can study by absorption, also one can study by resonance Raman as well. Of course, you can study the EPR and NMR as well for binding and other purposes. So, as I mentioned to you, these dioxygenases, intradiol oxygenases, are also like degrading the organic impurities. So, here we are not taking it as impurity, we are taking it as a reaction of a aromatic hydrocarbon. So, you can see that, and this cleaves and adds one oxygen into this, one oxygen into this. So, that is why you get the dicarboxylase. This is called cis mucanic acid. So, there are many things in the bacteria, in the life, convert into this part of the catechol, substituted catechol. It can come from this kind of a background where the methoxy, it can come from this where you can add OH here, this can come from here where you can add OH here, okay. This can come from this to this to this, and one hydroxyl, they add one more hydroxyl, is meta and then para, and can come from this. So, formation of this substituted catechol can be coming from the precursors, any of these, and thereby, so therefore, this is the kind of an impurity you will see which is called the protocatechuate, and this upon hydrolysis or breakage or addition of the O2, both the oxygens, it will break the double bond and give cis mucanic acid. Now, these enzymes are found in a lot of bacteria, and these enzymes are very robust. When will you say an enzyme is robust? Make a guess. The enzyme is thought to be or is expected to be robust when you show as a pH, it should be sustainable, temperature, it should be sustainable, all these kinds of things. So, if you can show these things, then you can say that that enzyme is robust, can work in. So, you can see here temperature. So, as you increase from 20 to 70, you get somewhere around 60 degrees Celsius. It is a very maximum activity is possible. So, around 50 to 60 or 60 degrees Celsius you have a activity is possible, high activity still. And now, if you go to the pH one, you can see as you increase the pH from 6 up to about 9, you have a peak point, then thereon drops. So, these bacteria will function on all these kind of molecules which were forming in terms of this protocatechate equivalent kind of a species that can be basically cleaved by O2. Of course, it's weighted O2 and then breaks this one and to oxidize to COOH and COOH kind of thing. So, now you understand the aromatic degradation. So, aromatic impurities are very common in water, very common in the industries where the dyes and drugs are synthesized, and therefore, the water is contaminated. So, one can use this even for degradation of the organic substrates. So, therefore, enzymes can be taken for their reactivity, for their and the reactivity can be converted into this kind of thing where you have the substrate, and the substrate is basically converted into that. Okay. So, you can see that, and these enzymes in the bacteria work at a high temperature like 60 and higher pH like 9. So, quite alkaline and high temperature are okay with this particular enzyme. These enzymes are a part of several bacteria. Now, let us look at some mechanistic aspects of this enzyme. We have looked at the mechanistic aspects of the previous enzyme, which is the cytochrome P450, and then we have looked at the one more enzyme, methane monooxygenase. In both the cases, only one O of the O2 is being utilized. Let us look at this protocatechate 3,4-dioxygenase, a dioxygenase case mechanism. Now, I mentioned to you it is a 5 coordinated center with trigonal bipyramidal having 2 tyrosine groups, and when a catechol kind of a moiety comes, catechol will bind, and this will give one proton to this, and the tyrosine metal bond can be tentatively disrupted. Okay. And this can give rise to a kind of a species of this type where both are bonded. In fact, both the monobinding initially followed by chelation have been identified based on proton NMR spectroscopy. When you have this way, you have more of a symmetry. When you have this way, you have less symmetry. Therefore, proton NMR is capable of talking about this. You can also use the EPR because you have ion center. Both the ion center as well as the EPR. EPR, you have to look at the basically the coupling values that can explain you in this. Okay, and people have looked at even the exorphs. Of course, they have looked at the resonance Raman of these species. What is the resonance Raman? It is the vibrational frequencies of the attached O or oxygen species or the substrate, which is studied by vibrational spectroscopy while passing a light which brings an electronic transition. That means, while the electronic transition takes place, that you are trying to study the vibrational pattern, because there is a vibronic coupling which will enhance the bands in the resonance Raman. I also said that based on the proton NMR, whether it is a monodentate binding or bidentate binding can be determined too. So, these are all very well worked out. So, what you do is you put some lot of these groups here which are hindering groups, then it will stop at the stage of the binding. So, therefore, that kind of things are studied by proton NMR and EPR. So, the binding and activation by chelation, and now this particular thing obviously is involved in the electron transfer, etc. And there are also some residues which are nearby which are protecting the thing. At this stage that you have an activated form of the ion 2, activated form of the ion 2 can take up the oxygen and form this kind of a species, and this species is active. So, it will break and one of the water will go, and you have your substrate, part of the, of course, the substrate into this through. Now, what is happening? The substrate now initially a catechol, now then it is becoming a semi-quinone in these steps and then becomes the quinone. So, you have a bis-quinone kind of a derivative. So, and this derivative can very clearly break down here and give the cis-muconic acid. So, that is shown over there and give this particular starting material kind of things. So, which is the protein where the ion is 5 coordinated with 2 of them tyrosines in this kind of thing. So, now do you understand how this takes place? You have activate by substrate binding, that should be always the first in all these oxygen activating enzymes. This oxygen should not be the first step, because otherwise immediately the oxygen get activated or oxygen bond gets ruptured, and then that can lead to the oxidation process to the enzyme. So, we do not want that. So, monodentated can bind, bidentated can bind. This has been very well studied by proton NMR and EPR spectroscopy, and this is now ready for electron transfer going into the 2, and then you have the oxygen being activated at this stage, and this is not so much stable, and so it will form a kind of a ring like structure with the product, and then that will open up and that will give the cis-muconic acid and the original molecule, original center of the ion containing center. So, now you understand that very nicely, everything is happening here. Now, earlier we have seen monooxygenase part, here we are seeing dioxygenase. Here no water goes out, because both the oxygens are added here, as you can see over there. Both the oxygens, one oxygen and then one more oxygen is added, and finally you get this kind of thing, breaks cis-muconic acid. So, substrate is being varied and studied. You can make the bulky and you can stop the reaction at the stage 2. You can study the charge transfer between the catecholate and the metal center, which has been studied. Then you have a semi-quinone radical like character, which is also studied and which is responsible for the activation of O2. Coordination through OH group has been deduced from EPR and NMR, EPR and NMR. 5 coordination during the reaction was supported by examples. O2 insertion followed by the sequence of reactions, and many of these have not been proven, but we have the things. And so, this part, that means we have seen 3 different enzymes. One is cytochrome P450, one is methane monooxygenase. Both of these are monooxygenases. Then we looked at one example for the dioxygenase, that is the protocatechuate 3,4 dioxygenase, and these dioxygenases are the kind of ones which break the aromatic organic aromatic substrates, because it can add both the oxygens. Same thing if you do by monooxygenase, will it happen? No, because it will add only one OH. So, therefore, there is no breakage of double bond, whereas this particular enzyme, dioxygenase enzyme, adds both the O2 and both directions. Now, look at for a while this particular scheme of the electron transfer. NADH, NAD plus is always there, then it will go to FAD, FADH2, then the 2 ion 2 sulfur, one more via 2 ion 2 sulfur, then at the reaction center. So, finally, at the this is the ion center, and that will add the electrons to that. So, electron flow, could you see? Could you see the mechanism of substrate binding, monodentate fashion, bidentate fashion, the quinone, internal intramolecular quinone, that will become the ion 2 plus. This ion 2 plus is ready for activation, and that will add the oxygen, and then that will convert into the peroxide, and then break into the one O, and that is O is introduced in this. No water goes away. The second O will basically break this and give this particular starting, and this is cis-muconic acid. So, in essential, we have studied 3 examples of the oxygenases: monooxygenase, dioxygenase, monooxygenase, the cytochrome P450, the another monooxygenase, methane monooxygenase, and the dioxygenase, all this. And dioxygenase are also well used from bacteria. You do not need to isolate the enzyme, just grow the bacteria and use the bacteria, incubate the bacteria with the water, and containing this kind of a thing, or sample containing this aromatic hydrocarbons, they will break and they will go into the soluble form. You know why? Because you are forming at the end the carboxylic, another kind of carbonyl carboxylic kind of a groups, therefore they are all very okay. So in the next class I will try to start with the dioxygen centers in reductase, phosphatase like hydrolase. So I have given oxygenase, what is left is phosphatase and reductase. These two will be taken in the next, I think, 3 to 4 classes or so, and then I will try to finish the this part of the iron enzymes. Maybe at least 3, 4, 5 lectures will be there. Thank you very much.